So, Industrial Gas Handbook, Gas Separation and Purification by Frank G. Carey. So, let's learn this. As practicing engineer, will not learn this. Okay, let's learn this. As a practicing engineer in the field of industrial gases for the past 65 years, 40 with L-year liquid and another 25 with a private consultant. On an international basis, I have encountered only 7 textbooks worldwide compiled for our industry. Even though the industry is over 100 years old, of the 7, 5-year edited by university professor or academic research scientist. The 6th was written in 1989 by the process manager of industrial company in England, which almost filled the bill but not quite. Those were published in England, 1 in France and 2 in the United States, 1 in Russia, with the possible expectation of 1 on process cycle established in England. Okay, so this is all about that. Let's not talk about author. Now let's go to table of content. Okay, so table of content is first chapter is gas separation and purification of industrial gases. So we'll learn about thermodynamics, basic thermodynamics, enthalpy, second law, Carnot cycle, entropy, irreversible system, third law, real gases, comparison, free. So we need to learn about this real gases and expansion bulb and adiabatic process, thermal chart, cryogenic properties of air. I think we'll be learning this, and refrigeration and liquidation system, liquefaction of system, high pressure free expansion and high pressure free expansion, cascade system, pre-cooling system, early development of industrial liquefaction system, heat exchanger, expansion machine, Lindell cycle. Okay, and air separation technology, first fractional machine. Beautiful. Liquid soft cooler, oxygen process, oxyton process, crude argon separation, source of helium, real normal gas. Okay, air separation technology. Chapter 2 is industrial application. Noble gas, front-end purification system, design for front-end purification system, process operation, safety, reference, product liquefaction, storage and transportation. This is important for us. Cryogenic prompt, this is also important to us. Cryogenic liquid vapors is important. Insulation, this is also important. Insulation of liquid storage, vacuum pumping, special gases, carbon monoxide, high purity nitrogen, carbon dioxide, ozone, methane, basic load natural gas, PNG, non-cyclogenic separation, cyclogenic equipment, material and machineries for the reading, compressor, product oxygen compressor, valve and valve station of cryogenic, safety and everything. Cleaning the oxygen system, cleaning agent, drying, testing, economics. Nice. Okay, so this is 539 pages long, and let's see how long this first second. I think it's a summary. So let's go through it, okay, because we might need in the future chapters and it is important. Gas separation and purification of industrial gases. Although cryogenic science and engineering fully developed in 20th century, it will be fruitful to review and refresh our memory with the various people who dictated their energies in uncovering the scientific purpose and technology, which today, from the basic foundation of low temperature liquefaction and separation of industrial gases, now are more elegant, known as cryogenics. One has to go as far back as the 18th century to uncover that in 1703 the work of a French physicist in thermometer and mathematics led to the supposition of the absolute zero. Also in 1720, Gabriel Bonne in Danzig developed the idea of temperature scale that bears his name, and wherein all the important numbers are divisible by 4 in 1741. Moreover, Celsius formulated the centigrade Celsius, better known as Celsius, with 0 representing the freezing of water and 100 representing the temperature at which the water boils. At this point, the discovery of diphlogisticated air or oxygen by Joseph in 1774 should be underlined. He reported his finding to Lazare in France, who wasted no time in repeating the preciously experiment and went even further to recognize that it was the active ingredients of the Earth's atmosphere. Priestley also discovered ammonia, sulfur dioxide, nitrogen, and a gas later identified as carbon monoxide. It was during the 19th century that serious attempts were made to liquefy industrial gases and to study their behavior as well as their characteristics. In 1823, Michael Faraday, then a young scientist at the Royal Institution of London, liquefied chlorine and studied the liquefaction and characteristics of ammonia. He also discovered that ammonia changes from liquid to its gaseous state by absorbing heat from the surrounding, thus lowering the temperature. Nice. In 1824, a young French engineer, Sadi Carnot, published his thesis Reflections, which became one of the pillars of thermodynamics. He demonstrated that a heat engine operating in a proposed ideal reversible cycle between two heat reservoirs, one hot and the other cold, would be the most efficient engine possible. This ideal cycle is universally known as Carnot cycle. In 1845, a little known Scot Thomas Andrews of Queen's College in Belfast, Ireland, experimented with the change of phase of carbon dioxide at various temperature and pressure and generated the first isotherm. These isotherms indicated that a gas cannot be liquefied regardless of pressure unless the gas is the first cooled to or below a critical temperature. The origin of the absolute temperature scale was due to the British physicist James, who experimented with the gases in the 1840 to confirm the efficiency of the Carnot cycle. In 1848, he wrote to William Thomas, a collegius, that his deduction was that the efficiency of Carnot cycle is proportional to 1 by T, where T is from the equation PV equal to RT. which represent the combined equation of Boyle and Charles, and T is based on T, the actual temperature of in degree Celsius plus 273. The sum T plus 273 was then known as the absolute temperature. Then in 1852, Thomas, later known as Lord Kelvin, formalized the efficiency of Carnot cycle for an ideal gas is W by Q equal to T1 minus T naught divided by T1 plus 273 equal to T1 minus T naught divided by T1. After a long series of experiments with hydrogen, Joule and Thomas announced in 1862 that the difference between the above mentioned absolute scale and the air thermometer was insignificant. After experiment with helium, which was found closer to an ideal gas than hydrogen, 273 became 273.15 with slightly more additional correction as the temperature dropped below minus 20 degrees Celsius, equivalent to Kisomo, and I don't know how to pronounce. During 1850, William Thomas, followed by Rudolf Celsius in 1851, articulated the first and second law of thermodynamics. According to 1865, a young German engineer, Carl Lindell, designed a refrigeration machine based on the Carnot cycle and achieved low temperature by vapor compression. I think this is important. Carl Linden designed a refrigeration machine based on the Carnot cycle, achieved low temperature by vapor compression. When vapor is compressed, it will be low temperature. Nice. Using the same principle and spiral wound counterflow heat exchanger designed by William Hampson of England, Lindell built the first industrial air liquefaction machine in 1895. At this point, it should be noted that in 1851, an American physician named John Gorey patented the first ice-making machine using the compression and expansion of air to generate refrigeration. This patent model is still in the National Museum of American History. In 1873, Johannes van der Waals developed an equation of state that offered an explanation of the critical phenomena in the change of state and fitted nicely with the observation of isotherms of Thomas Andrews. Van der Waals used the valves of pressure, temperature and volume divided by the critical values. This led to the law corresponding state, which enabled James Dewar and to determine the necessary data for liquefaction of gases. In 1877, a French Louis Paul announced the liquefaction of oxygen. He used a glass capillary tube with thick walls wherein gaseous oxygen at 200 to 300 bar was cooled to 245 Kelvin by evaporating liquid sulfuric acid. After releasing the pressure almost adiabatically, the drop in temperature was significant to cause the formation of mist of liquid oxygen. So we'll learn up to here and we'll continue in next class. Thank you for watching. See you another video. Bye bye. Take care.